this work, we present a new model for the alignment of event data, the spatio-temporal Poisson point process. Event cameras provide a natural and data-efficient way of capturing visual information. The way of acquiring this visual information, however, differs significantly from traditional frame-based video recordings, where frames are recorded at a fixed rate, usually 30 frames per second. Events, in contrast, are triggered by local brightness changes, which can occur due to the relative motion of the camera and the scene, changing light conditions, or moving objects. In this work, we focus on static environments with a moving camera. On the left, we can see an event stream recorded by an event camera. As the camera moves, events recorded at a single sensor location correspond to different world points in 3D. This results in a blurred projection of the events onto the image plane. Projected events are pictured here in black. To extract meaningful information from event cameras, it is very helpful to register those events that are triggered by the same underlying world point. Aligned events are shown on the right. Their projection results in a sharp contour image, which lets us identify objects more easily. The basic idea of our approach is that we develop a model for the data as though it has been perfectly aligned already. The observed data is a set of events recorded by a moving camera over a time period delta t. For the aligned data, we consider events as though they have been perfectly aligned with a set of ground truth transformations that invert the camera's motion. We now introduce our probabilistic model for aligned event data and describe how it can be used to align observed events. We first consider a model for events that are aligned at a single pixel location. We model this with a Poisson point process with a rate parameter lambda. This implies that the number of events occurring at a particular pixel location x is a Poisson random variable with rate parameter lambda. Next, we model the entire aligned data as the output of several independent Poisson point processes, each with a separate rate parameter lambda depending upon its location. Due to the spatial independence of individual Poisson point processes, we can multiply the probabilities of observing k events at each individual pixel location. This model naturally leads to an optimization problem. We search for the set of transformations when applied to each event that maximize the likelihood for the transformed data under our model. In particular, we estimate the camera rotation that leads to the best event alignment. Here, we define R as the mapping that applies a rotation to an observed event at a particular location and a certain time t. While various families of transformations can be considered, we focus here on constant angular velocity transformations. This simple maximum likelihood approach directly corresponds to minimizing the entropy per pixel.
For experiments and evaluation, we use a publicly available dataset called DEV240C. It consists of video sequences with diverse camera motion. We evaluate our approach on sequences boxes, poster, dynamic, and shapes. This figure shows qualitative results for all approaches used for comparison. We show the aligned event image using IMU together with a detailed close-up view for each approach, highlighting the alignment quality. Our approach constantly reconstructs sharp object contours, which is an indicator for precise alignment. The table shows a quantitative comparison among state-of-the-art methods for angular velocity estimation. Compared to the next best performing method, on poster and boxes, our approach shows an improvement of about 5% measured based on the root mean square error. On the other two sequences, we show improvement of 4% and 39%. The gain of such improvement in particular shows our superior performance for event recordings, where the scene structure and motion varies significantly. One advantage of STPPP is that it has the same computing complexity but much better performance in terms of the root mean square error measure than contrast maximization. The complexity of our approach as well as for contrast maximization is linear with the number of events. The complexity of entropy minimization is quadratic with the number of events since it requires the cost computation of all event pairs. The approximate version of entropy minimization only considers the costs of events within a certain distance defined by kernel. Thank you very much. Our code is publicly available. Feel free to try it out.